Hey everyone, and welcome. Today, we're going to break down a concept in optics that, let's be honest, trips up a lot of students, but it's actually super simple once you see it the right way. We're talking about the normal to a curved surface. So let's just get right into it.
And you know what? This is 100% true. If you can really truly get what the normal on a curved mirror is, and more importantly, how to draw it, the entire topic of reflection just clicks. It becomes so much easier. So let's crack this code together, shall we?
All right, first things first. Before we even start thinking about crazy curved surfaces, we've got to go back to the basics. So what exactly is a normal?
Okay, it's really just a fancy word for a straight line that stands at a perfect 90-degree angle to any surface. Think about it like this. You put a pin on a flat table. If that pin is standing perfectly straight up, not leaning left or right at all, that pin is your normal. It's that simple.
Now, what happens if you stick a whole bunch of these pins on our flat table? What do you see? Well, they're all standing straight up, right? And they're all parallel to each other. This is a really key idea to lock in. For a flat surface, every single normal points in the exact same direction.
So this is where it gets really interesting. What happens when we stop thinking flat and we start thinking curved? You know, just like the concave and convex mirrors you're studying. Let's imagine our flat surface is actually a piece of foam, and it's got all those parallel pins stuck in it.
So let's ask a question here. If we take that piece of foam and we start to bend it, what do you think is going to happen to all our little pins, which, remember, are our normals? Are they going to stay parallel? What's your guess?
No way, they won't. The moment you bend the foam, the surface under each pin changes its angle. And since each pin has to stay at 90 degrees to the surface right below it, they all start changing direction too. All of a sudden, our neat parallel lines are pointing all over the place.
And this is where the magic happens. This simple act of bending the surface reveals a very special, almost magical point that is literally the key to understanding everything about curved mirrors.
Okay, so imagine we take our foam and we bend it inwards, kind of like a bowl or a cave, a concave shape. Now look at those pins. They're not parallel anymore, are they? They've all started leaning inwards, kind of pointing towards each other.
And if you bend it just right into a perfect smooth curve, something amazing happens. All of those pins, all of those normals, they will all point towards and meet at one single special point in space. This isn't just a random coincidence. This is the pure geometry of a circle at play.
And that special point? Well, it has a name, the center of curvature, and we label it with a capital C. And why C? Because any curved mirror is really just a tiny slice of a giant imaginary sphere, and point C is the dead center of that big sphere. So that means every single normal is just a radius of that sphere.
And hey, just to complete the picture, what if we bend the foam the other way, outwards, to make a convex shape? Well, you guessed it, the exact opposite happens. The pins, our normals, they all point away from each other. They spread out, or as we say in physics, they diverge.
So here's the crucial takeaway. We can now take this really simple idea of foam and pins and apply it directly to those ray diagrams you see in your textbook and exams. Let's connect this to the official terms you need to know.
First up is the pole, which we label with a P. This is super easy. It's just the exact middle point on the shiny surface of the mirror itself. You can kind of think of it as the mirror's belly button.
Next, we've got the principal axis. This is like the main road for our diagrams. It's the most important reference line. It's just a straight line that runs through both the pole P and that magical point we just found, the center of curvature, C.
And finally, the radius of curvature, or R. This is simply the distance from the pole P on the mirror's surface all the way to the center of curvature, C. It's literally the radius of that giant sphere that our mirror is a small part of.
Okay, fantastic. We've got all these definitions down, P, C, R, but why? Why did we spend all this time talking about the normal? Why does it matter so much when we're trying to understand reflection?
Because of this, the single most basic fundamental law of reflection says the angle of incidence equals the angle of reflection, right? But here's the catch. Both of those angles are measured from the normal. If you draw the normal in the wrong place, your entire calculation, your entire diagram will be completely wrong. The normal is the starting point for everything.
And this shows you exactly what happens because of that. Since the normals on a concave mirror all point inwards, they force parallel rays of light to reflect inwards and meet at a point. They converge. And because the normals on a convex mirror point outwards, they force parallel rays to spread out and diverge. You see? The normal dictates the entire path of the light.
All right, let's wrap this all up and make sure you get full marks on this topic. I'm going to give you some quick and simple exam tips and point out some really common mistakes you should try to avoid.
Okay, definitely look out for these. The absolute biggest mistake is thinking the normal is always a straight up and down line. We now know that's only true for a flat surface. Always use point C to find your normal. Always draw the normal before the reflected ray. And please don't forget to put arrows on your rays to show which way the light is going.
So, here's your foolproof 4-step process for the exam. Step 1. Find your center of curvature C and the exact point where the light hits the mirror. Step 2. Draw the normal by simply connecting C to that point with a straight line. Step 3. Clearly label everything. P, C, the principal axis. And finally, Step 4. Now and only now you can apply the law I equals R using that normal line as your reference.
Look, if you remember only one single thing from this entire explainer, please let it be this golden line. Write it down, memorize it, understand it. The normal is just the line from the point on the mirror to the center C. That's it. That's the entire secret.
And there you have it. Seriously, if you've truly understood this one concept, believe me, the rest of optics is going to feel so much easier. You've just built the perfect foundation for yourself. Thanks so much for watching.